All right, so welcome back. Today in this video, we're going to be continuing our review in the water resources and environmental engineering section for the Civil FE exam. So today we're going to be looking at pumps, have a few practice problems for you all, and I want to go ahead and get right into it. All right, so number one says, water is to be pumped at a flow rate of 0.03 meters cubed per second. Find the head loss due to flow of the pump. Ignore minor losses. All right, so I see point A gives us the elevation, and then it goes through the pump and up, shoots up. They give us the length of the pipe shooting up. They give us the diameter of the pipe going up, and they give us the F, which I believe is a friction factor, but don't quote me on that. And then they give us the elevation at point B, right? So let's take a look at this. So what information are we given? All right, start with the given information. Well, they give us the flow rate of the pump. They give us the pump length. Or the length of the pipe. They also give us the diameter of the pipe. They give us, I'm going to say, the friction factor. I think that's what F stands for. And they give us the elevations at the water levels. The elevation of water levels. Okay. So, what are we trying to find? Well, it says find the head loss due to flow. Head loss due to flow. And we're not going to take into account the minor losses because it says to ignore the minor losses. Right? Ignore minor losses. Okay. So what formulas do we need? Well, I'm going to search head loss. Okay. HF is the head loss. Okay. So given the information, see pressures here. We're not given any pressures, so I'm gonna keep going. So this one says head loss due to flow. All right. So this is probably the area that we need to be in. Take a closer look. And we can see what information we're given. So HF is the head loss due to flow. What is F? What is F? F is the friction factor, which I believed I said. Okay. D is the diameter of the pipe. Got that. Do we have L? L is the length over which the pressure drops. We have L, which is 300 meters. And then do we have V? No. Do we have G? G should just be gravity, which is 9.8 meters per second. Okay. All right, so looks like we're missing V. So we'll just write out the information that we're given. So we have, so HF is equal to question mark. We have F here. We have L here. We also have D here. V is equal to question mark. We have G, which is equal to 9.81 meters per second squared. Okay, so the only thing we now need is we need V and H of F. And the main thing that we're solving for is head loss, right? So can we get V from the information that we're given? We also have, so we have Q, which is 0.03 meters cubed per second. And we have, there's this formula, just important for you to know, that if you have flow and if you have an area, then you can find V. So it's the continuity equation. So as long as the flow is continuous, which it is, being pumped, Q is equal to A times V. So if I have, what would A be? Well, A is the cross-sectional area of flow, right? So you got this, we got this pipe, right? The cross-sectional area would be that section right there, right? They give us the diameter. We know that the flow is being shot up that way continuously. So we know that we can also use Q is equal to A times V to get our velocity. All right, so first solve for that. So we'll just say Q is equal to A times V. What is A? So A is equal to pi r squared, right? That's the area of this circle, or the cross-sectional area. So what is R? Well, we want to make sure that we put everything in meters. So R is equal to D divided by 2, right? Or our diameter divided by 2. All right, so we'd say R is equal to 200 millimeters divided by 2, which equals to 100 millimeters, or 0.1, right, meters. Okay, so I know my R. So A is equal to pi times 0.1 pi r squared, right? So A is going to equal to 0.0314 meters squared. All right, so Q is equal to A times V now. So Q, which is 0.3 meters cubed divided by seconds, is equal to 0.0314 meters squared. Do you see why we wanted our stuff in meters? It's going to give us a velocity once we divide in the correct units, right? Our units are going to cancel, right? Meters squared, meters cubed. This is going to leave us with meters per second, all right? So we'll get, for this one, V is equal to 9.549 meters per second. Okay, we have V now. So I can say that this is no longer a question mark. V is equal to 9.549 meters per second. Okay, so what is H of F? We know that head loss. We're going to go back to our equation. H of F is equal to F L over D. I'm just pulling this equation. L over D, V squared over 2 times G. Okay, so now we just plug and chug all of our information in. So H of F is equal to L is 300 meters. All right, I forgot something. We're not starting with L, we're starting with F, right? So F is going to be 0.003 times my 300 meters divided by 0.2 meters. So we know that that's like my diameter, right? So L over D times my V, which is my velocity, which is 9.549 meters per second. We're doing all that squared, right? Divided by 2 times 9.8 meters per second squared. All right, and we get H of F is equal to 20.9 meters. So our answer is going to be B. So remember, if you're given flow or if you're given an area and a velocity that's going through pipe, then you can get your Q, which may help you into solving even more, especially for head loss. Like sometimes you need, most of the time you're going to need V, or they could ask you, a few different ways. Maybe they make you solve for the length of the pipe and they give you all the other details. All right, but being able to substitute for variables and take the information that they give you is very crucial. All right, let's look at number 2. All right. So if a pump has a hydraulic power of input of 18 kilowatts and a shaft input power of 22 kilowatts, calculate the pump efficiency. All right. So with this information, we're given hydraulic power and shaft power, right? And so we're trying to find pump efficiency. All right. So I'm just going to do a pump. It's going to search pump efficiency real quick to see if I can find anything. All right. So pump efficiency is N of pump. So it's from 0 to 1. Pressurize fan power. Okay, so with this doesn't really help us here. So based off the information that I'm given, right, I'm given that you have a shaft that can go up to 22 kilowatts. And I know just from prior knowledge, right, there's some prior knowledge that you're going to need to know. But just based off of this, right, if I have a shaft and it can go up to 22 kilowatts and my hydraulic power can do 18, then I would say, okay, I know that power efficiency only can efficiency is going to be a percentage where the max is 100%, right? And so if the highest it can go is 22 kilowatts and the hydraulic power that's going into it is going in at 18 kilowatts, then I know it's not going to be 100%, but how efficient can it be, right? I'm going to say 18 divided by 22 to give me 0.818 or 81.8%. So this one was more of like a prior, kind of like a prior knowledge using logic to get an answer. All right, let's look at number 3. For steady one-dimensional flow, which is constant, mass flow rate, flow velocity, cross-sectional area, or none of the above. So given steady 1D, sounds funny saying it, but one-dimensional flow, find which is constant. All right, so let's look up mass flow rate. All right, so I'm just reading, making sure that I don't see anything dealing with one-dimensional flow. Heat exchangers, that's the section I'm in. HVAC. Mechanical engineering. Vaporized liquids. Thermodynamics. Okay, one-dimensional flow for mass flow rate. Okay, so I'm just reading up under. For steady, one-dimensional flow, m dot is constant. Okay. So m dot is mass flow rate. So I know that A is going to be my answer. All right, so this concludes the pump section of the water resources and environmental engineering section. In the next section, we're going to be looking at water distribution systems. See you in the next video.